All right, so problem 9, it says, let x represent the number on the face that lands up when a fair six-sided number cube is tossed. The expected value of x is 3.5, and the standard deviation of x is approximately 1.708. Two fair six-sided number cubes will be tossed, and the numbers appearing on the faces that land up will be added. Which of the following values is closest to the standard deviation of the resultant sum? They seem number cubes to be, really, I guess, formal. But, we're just thinking about dies. A die has, 1, 2, 3, 4, 5, 6. Has the numbers that can come up are 1, 1, 2, 3, 4, 5, 6. I'm sure most of you played, Monopoly or something, but just in case you need a little review. So the expected value is basically the mean. If you were to roll the dice twice, what would the mean be? So we're finding the where did it say the sum we're being added. So let's let x1 be the number that appears on the first roll, or the first die, and x2 be the number that appears on the second die. And so we see the expected value, or we can say e of x, is equal to the number on the first die plus the number on the second die. And this is equal to 3.5 plus 3.5. The expected value be 7. Now, standard deviation is a little different. Expected values you can add, but let's have the standard deviation of x. Remember, or the variance of x. We have to first find the variance. And once you find the variance of the sum, we just take the square root. So the variance of x when you're rolling in this case, when you're adding the numbers up, you just add up the variances. So we'll add up the variance on die 1 when you roll it, plus the variance on die 2 when you roll it. I probably should use a different thing than x, but let's just make sure that we know that these are 3 different things. So the variance is going to be 1.708 squared. And then whatever this is, we just take the square root of, because we want to find the standard deviation. Standard deviation of x is the square root of the variance. So let's figure out what this is. Times 2. So we have 5.834528. Then we take the square root of this. And we get about 2.415. And so the answer is C. I hope that I didn't make this explanation was okay. But let me just give you a formula so let's say if you remember something from random variables, basically you'll see like expected value of t. It will maybe if you just to refresh your notation, maybe you see like t is the sum of adding the variables, and then so the mean of t, or the expected value of t, would be the mean of x1 plus the mean of x2. And then the only thing you have to remember is that with the standard deviations, you can't simply add them, but you can add the variances and then take the square root, which is what we did here. But this is a very confusing chapter. So just let me know if you have any questions on that, because probability is something I've learned that it's hard for some students to understand without a lot of examples. But anyways, problem 10. Based on previous research, the standard deviation of the distribution of the age at which children begin to walk is estimated to be 1.5 months. A random sample of children will be selected, and the age at which each child begins to walk will be recorded. A 99% confidence interval for the average age at which children begin to walk will be constructed using the data obtained from the sample of children. Of the following, which is the smallest sample size that will result in a margin of error of 0.1 month or less with a confidence interval? Okay, so remember that when you have a confidence interval, you start with a point estimate centered in it in the middle. In this case, our point estimate will be our sample mean, x bar. And from that, we add and subtract the margin of error to get the endpoints. Add it to get the positive side and subtract the margin of error to get the negative side. In other words, this distance here is equal to the margin of error. Now, for estimating population means, we take our sample mean and we add and subtract our significant value, t star, times the sample standard deviation over the square root of n, because this is just the standard deviation for the sampling distribution. So if you see this formula, this is what we're going with. However, in order to have t star, you need the sample size. So instead we use the z star. So again, this whole thing is just plus or minus, in this case, z star times the sample standard deviation of this over the square root of n. And this side you subtract that. So we only care about this. So that's a little overview. So we set this equal to, or I guess we could say less than or equal to 0.1. So we go 0.1. This is our margin of error. 0.1 will be greater than or equal to z star times this sample standard deviation, which will be 1.5 over the square root of n. Now to get a z star, we can just look at our table, or you can use your calculator and look for the corresponding z value that gives you half a percentage on each side to the area of 0.005. And you'll get about negative 2.58 on the left and positive 2.58 on the right. So z star will be, let's just use 2.58. And so you're just solving this inequality. So make sure you know how to do that. So what we can do is multiply both sides by the square root of n, divide by 0.1. And do some algebra. So there we'll get 2.58 times 1.5 divided by 0.1. But since we have the square root of n, we're going to need to square both sides. So we're going to square this, and we'll get about 1498 or 1497.69. So we need a sample size of at least this number. So the closest one will be 1600, and you have to be conservative. So even if we had like 1400 versus 1600, you would go with a higher one. And that's all there is to that. And again, feel free, leave comments and give me feedback if I'm going too slow or too fast, or I'm just not doing a good job explaining these, because I kind of want to go through each one in detail in case you need a little review. So I know some of the problems I may take more than a few minutes, because and there's a lot of like context and statistics, but just let me know. So 11, let x be a random variable that has a skew distribution with mean 10, standard deviation 10, and based on random samples of 400, the sampling distribution of X bar is. Okay, so this is just really a conceptual one. So the X bar, the sample means are unbiased estimators. So the mean of the sampling distribution of X bar will be equal to the population mean. So it'll be 10. And the standard deviation of the sampling distribution of X bar will be equal to the sample or the population standard deviation, my bad, sigma, over the square root of n. So in this case, that'll be 10 over the square root of 400, or 10 over 20, which will be 0.5. So right away, we know it can't be the first two, or C or D. So it's down to C and E. And it's going to be E because it's also going to follow the same shape. So it's going to be E because the shape is going to still be approximately normal. All right. Number 12, the number of hurricanes reaching the east coast of the U.S. was recorded for each of the last 10 decades by the National Hurricane Center. Summary measures are shown below. Okay, so let's draw a graph of this so I can see our box plot. Looks like we got the 5-number summary. So 12, 24, median is 16. Q1, or the lower quartile, is 15. Upper quartile, or Q3, is 18. So if we made a box plot, this would be our box. Now, it looks like we need to know which ones are outliers. So if you remember the outlier rule, we typically use like a 1.5 times the IQR. The IQR is the distance from Q1 to Q3. Q1 to Q3 is just 15 and 18, which is just 1.5 times 3, which is 4.5. So we want to see if the distance from Q3 to the endpoint is at least 4.5, and here it's 6 actually, and or if the distance from Q1 to the minimum is again less is at least 4.5, or in this case we're subtracting 4.5. This is only 3-way, so this is not going to be an outlier. But this is 6-away, so 24 would be an outlier. Now, we know 24 could be an outlier, and the key here is to recognize that there are 10 values in here, and it's possible that you have other values in here that are like 23, or you can have a couple other values there. You can have multiple values that are 23. We don't know how many values. We don't know the concentration of the numbers between 18 and 24. All we know is that the maximum is 24, but the pointer below it could be, again, 23, or there could be multiple 24s actually. So that's what they're trying to test you on. So think of it like this. Think of it like you have let's say 1, 2, 3. You have your data set just maybe has a couple 24s in it. Maybe it has all you need is more than one. You could have 2 or 3 24s, and now you would only show one endpoint on your graph. You can't tell from the box plot how many 24s you got. So then our answer would be E, because there are possible outliers that could be on the high end. All right. Makers of a new pain relieving medication claim that it relieves chronic pain faster than the current top-selling pain reliever on the market. A double-blind experiment was conducted in which 10 people who experienced chronic pain were randomly selected to take either the new or the current medication. Each of the 10 people recorded the time in minutes from taking the medication until pain relief. After an appropriate time period, each of the 10 people took the other medication and recorded the time from taking the medication until pain relief. The medication each person took first was randomly determined. And because both medications looked the same, the people in the study did not know which medication was taken first. Here's the table that shows the summary statistics. So which of these values is closest to p-value? So this is going to be where we use a significance test. And since we're looking at sample means, we're going to use a t-test where we have our equation x bar minus the null hypothesis value over the sample standard deviation over the square root of n. Our sample mean was negative 0.425. Our null hypothesis would be 0 because our null hypothesis is basically saying that the new medication doesn't provide any more relief than the current medication, which means that the difference would be 0. Sample standard deviation, we would look at this. And sample size is n, so all over the square root of 10. If we do the math, we'll get about negative 0.9634. Now, we have to use our table, pretending you don't have an advanced calculator, which I am going to pretend that. And also make sure we know our degrees of freedom is 1 less than the sample size. So it's going to be 9. The degrees of freedom of 9. And we look in our table in the 9th row, because it lines up in 9. And we look for the t-star value or the t-value that's closest to our 0.963. And it's going to be between here and here. It's not going to show it exactly because it's impossible to, it's not going to be possible to show every single number. So we look at the probabilities corresponding to that, which means our probabilities would be somewhere between 0.15 and 0.2. Between 0.15 and 0.2, and that would then be A, because 18% is between 0.15 and 0.2. And that's all there is to it. All right, number 14. Which of the following graphs represents a binomial distribution with n equals 20 and p equals 0.25? Okay, so this is like a theoretical one. Again, going over random variables. And the first thing to remember is that the mean of a random variable is n times p, which in this case will be 20 times 0.25, which will be 5. And this is where the distribution will be centered at. So the distribution will be centered at the mean, which looks like we already kind of eliminate a lot of these. Maybe mean the only ones, it would come down to A and C, I would say. Those are the only ones you could argue that the mean or median, or it'd be centered at 5. So now, like, which one would it be? Well, a binomial distribution would follow a normal distribution as n goes to infinity. So we say it could be approximately normal as n as the sample size goes to infinity. So this would be our answer. This is what would be a geometric distribution. Because as geometric distributions, if you remember, it's basically the probability of getting your first success. So as the number of trials goes up, the probability of you getting a success on that trial goes down. It's like you flip how many times you have to flip a coin before you get a first heads. You know, it could be 1, 2, 3, 4, 5. So it's not going to be A, it's going to be C. Now this concept is kind of advanced again. Some textbooks present it very abstractly, some present it very basically. But again, just let me know if you want me to go over this formally, because there's a lot to this. Okay, so I'm going to stop this part of the video here. But again, let me know what you want me to focus on. And I'll see you guys in the next video. Bye.